In the world of numbers, every fraction tells a story. Some are short and simple, they end with grace like 1 half becoming 0.5. Others are eternal wanderers looping endlessly like 1/3 echoing 0.33 forever. But as programmers, we must tame these infinite dances. We place boundaries, we capture cycles, and we wrap eternity inside parentheses. Today, we embark on this journey to convert fractions into recurring decimals and bring order to the infinite. The problem is simple to state yet elegant to solve. We are given two integers, numerator and denominator. We need to represent their division in decimal form, not just for terminating decimals but also for repeated ones. If the decimal part repeats, we must identify the cycle and enclose it inside parentheses. For example, 1 divided by 2 gives us 0.5, clear, finite, and done. 2 divided by 1 is simply 2, but 4 divided by 333 results in a repeating sequence 0.012 with 012 inside parentheses. Our task is to detect such repetition and represent it properly. The constraints sets the boundaries of our problem. The numerator and denominator can vary in a large range, as small as negative 2 billion or as large as positive 2 billion. But the denominator will never be 0. That's our one safeguard. These numbers can be tricky. They may cause integer overflow during calculations if not handled carefully. They may also carry negative signs which must be managed clearly. And finally, the output string must remain less than 10,000 characters, so efficiently matters even for repeating decimals that go on forever. At first glance, division seems easy, but this problem has hidden complexities. The key challenges are detecting repetition, inserting parentheses, handling negatives, and preventing overflows. When does a remainder cycle back? That's the heart of the problem. Where exactly should we mark the start and end of the repeating part? A negative numerator or denominator should be reflected with a proper sign in the result. Large values could break normal integer operations. If we miss one of these, the solution fails. So we must build a careful step-by-step approach. Our solution follows a structured approach. First, check for zeros. If the numerator is 0, the result is simply 0. Second, determine the sign. If numerator and denominator have opposite signs, the result should start with a minus. Third, convert to long. To handle edge cases like int min, we work with larger data types. Fourth, divide for the integer part. Perform the division once and append it to the result string. Fifth, check for remainder. If none exists, we can return the result immediately. Sixth, process fractional part. Simulate long division by multiplying the remainder by 10, dividing and appending zeros. Seventh, track remainders. Use a map to record where each remainder first appeared in the result. And finally, last, detect cycles. If a remainder repeats, we know where the cycle begins. Insert parentheses there. This process captures both terminating and recurring decimals. Let's look at the code. First, we handle edge cases. If the numerator is 0, return 0. Next, we decide the sign. If one is negative and the other is positive, we add a minus sign to the result. Then we convert both numbers into their absolute long equivalents. This protects us from overflow in cases like dividing negative 2 billion by 1. Now comes the integer division. We compute the integer part and append it to our result string. If there is no remainder left, we can stop here and return. If a remainder exists, we know we must process the fractional part. We append a decimal point. Now the key is to track remainders. We use an unordered map, sorting each remainder along with the index of the result string where its corresponding quotient was placed. Here's the trick. Multiply the remainder by 10. Divide by the denominator to get the next digit. Append the digit to the result. Update the remainder. If at any step the remainder becomes 0, the division ends and there is no repetition. But if the remainder is seen again, that means we have entered a cycle. The map tells us where the cycle started and we insert parentheses at that position. Let's test our approach with numerator 4 and denominator 333. Integer division 4 divided by 333 gives 0 and a remainder of 4, so we start with 0. Multiply remainder by 10, we get 40. Divide by 333 gives us 0 and we append 0. Then we multiply remainder by 10, we get 400, and divide by 333 gives 1. So we append 1. Remainder now is 67. We multiply by 10, we get 670. Divide by 333 gives 2. So we append 2. Remainder 4 again. At this point the remainder repeats, meaning we are in a cycle. The digits 0, 1, 2 form the repeating sequence. Final result is 0.012 with 0, 1, 2 within the parentheses. Now let's try 1 divided by 6. Integer part 0. Start with 0. Remainder is 1. Multiply by 10. Divide by 6 gives 1. Append 1. New remainder is 4. Multiply by 10 we get 40. Divide 6 gives 6. Append 6. Remainder is again 4. So the cycle is detected. So the repeating sequence is just 6. Final result is 0.16 with 6 inside the parentheses. And there we have it, a complete solution to the fraction to recurring decimal problem. We combined mathematics with programming precision by simulating long division using maps to detect remainders and handling edge cases with care. We successfully represented both terminating and infinite decimals in a finite string. This problem reminds us of something profound. Even infinity, when observed carefully, carries pattern, and with logic we can capture and represent them beautifully. Thank you for your attention.